K8byp on a lazy Tuesday. Let's look at a real annoying thing that transistors do. You might have cause to take a small milliwatt output RF generator and want to put on a simple transistor amplifier for 100 milliwatts or a watt or so. And if you don't use high frequency transistors, you'll get bit in the behind by something called C sub OB. Here's a simple circuit of a transistor amplifier, generator on the left, coupling capacitor, high value, 1000 puff or more, low reactance. A maybe 50 to 100K base resistor leaking current into the base to the emitter, and a collector resistor and voltage out. On DC, we get the resistors for class A, so the V out with no signal applied is half the supply voltage. And everything's happy. Everything's happy until we change the biasing to go to class B, and suddenly the input shorts and there's no output or badly distorted output. And what's happened is we've gotten bitten by the C sub OB bug, which is the capacitance that is implied across the base to emitter junction, but only when it's either off or reverse biased. There's our little enemy C sub OB through switch. A negative going half cycle that turns off the base emitter junction. C sub OB is in circuit. And when it's charged, it does screwy things to the base emitter diode. And the dashed lines around the diode imply an ideal diode. That's purely the diode function without any stray values. What we end up with is R sub BE in parallel with C sub OB. And what that effectively is a switch that on a positive half cycle closes the circuit to the base emitter resistance and opens the circuit to C sub OB. And when there's zero bias or negative going, which reverse biases a diode, that resistance opens up, and there's that capacitance. Now, on top of package capacitance, there's also that C sub OB, and for poor low frequency switching transistors that are not really intended for RF, that capacitance might be upwards of 1,000 picofarad. How can that be in such a tiny semiconductor junction? Well, the capacitance formula is basically A area divided by D, and inside that transistor, the pieces of semiconductor have metalizations bonded to them. And those are the contacts between the leads and the pieces of silicon and junction. And those are capacitor plates. They're extremely tiny. You'd think there'd be no capacitance, but the thickness of those silicon areas is extremely tiny. Micrometers, thousandths of an inch, whatever. So that makes a little area divided by an extremely tiny D, and that C sub OB can be upwards of 1,000, maybe 2,000 picofarad. And that transistor is no good for RF much above 100 kC. So to get a transistor for RF use, we have to first select one with very low capacitance, and you'll notice on the graphs for C sub OB that's voltage dependent. At 1 volt, the capacitor might be 300 picofarad, and at 5 volts, it might be 10. And we might like the 10 picofarad figure, but we can't get there without a significant reverse voltage on a transistor, and many transistors can't take much more than 5 or 6 volts reverse. They go boom because the voltage tries to pull the junction apart. And here's the typical curve for capacitance versus voltage. As the base emitter voltage negative, that should be a minus V. As the reverse bias goes up, the capacitance goes down, and it's kind of an exponential curve. So what that capacitance is doing is it is trying to keep the junction reverse biased, even when the bias tries to take it forward, and it causes distortion in the waveform. So if you look at RF amplifier circuits, you'll also often see an RF choke across the base. RF choke is open to RF and a short to DC, and what that does is that gives that capacitance a discharge path when that implied switch closes to connect that C sub OB across the base to emitter. And you see the BE resistance isn't there because the diode's off. So that's okay for low power and low frequency, but modern practice is to use MOS devices, which have extremely low capacitance, on the order of maybe a couple picofarad at the most, because of the way the gate to source region is made. So these are the puppies that tend to be used for RF power applications above a few watts. So this also applies to diodes, because the base emitter junction is a diode. So there's the pitfall with transistor biasing and RF and how to get around it. K8byp Bit.